In this lesson, we will be learning about thermochemical equations. So what we have here is that there's heat coming from a chemical equation. Okay, so this includes the heat for stoichiometric quantities. Stoichiometric of the reactants and products. Let me show you an example. So here we have an equation where ice is melting. It used to be solid on this side, on the reactant side, and now it's liquid, it's melting. When ice melts, is it endothermic or exothermic? Yes, you're right, it is endothermic. So you're putting any energy in. The delta H is the heat that you need. It's the same as Q, or the heat that you need to heat up or melt that solid water or ice. It is the delta H is 6.01 kilojoules. Okay. What this means is that if you had 1 mole of ice turning into 1 mole of liquid water, you're going to need 6.01 kilojoules. If you're going to if you have 2 moles of ice, you're going to need double the amount. 3 moles of ice will need triple the amount. Okay, so this is a thermochemical equation because it follows the mole or the stoichiometric quantities, the amount that you have. Okay, here's another example. Burning methane. While the gas is burning, is it endothermic or exothermic? Well, heat is being involved and light, so it's going to be exothermic. Therefore, the heat of the reaction, or delta H, or the enthalpy, is going to be negative. That is the heat. Okay, for this reaction, it shows that this is already balanced. You have to balance the equation, of course. You're burning methane. This is methane. You use oxygen to burn it, and you're going to make CO2 and H2O. There's a 1 right here and a 2 right there. And a 1 there and a 2 there. So this relates to the stoichiometric quantity. If you have 1 mole of methane, just box this equation, 1 mole of methane, you're going to give off this much heat. If you have 2 moles of methane, you're going to double that heat. Now, if you happen to measure the heat and you only got half the amount, what does that tell you about the amount of methane? That's correct. You will have half the moles. Okay, so with this heat of the reaction, and you know how to get the heat of reaction. You use a calorimeter, and you did that in the lab. Once you get that, you'll be able to calculate backwards and know how much you have. Okay, a property of thermochemical equations is that if you reverse this, if you reverse the reaction, you also reverse the sign. Obviously, if it was exothermic and you reverse it, then it's going to be endothermic. Let's go ahead and look at the ice equation. When you melt it, you need to put energy in. What if you flip the equation? This case, what's the opposite of melting? That's correct. You are freezing. Okay, so is freezing endo or exo? So if this is exo, then the opposite would be endo. No, I'm sorry. Positive is endo because you're putting heat in. So the opposite of endo would be exo, which makes sense. To freeze liquid, you have to take energy out of it to turn into solid ice. Okay, so the problems for these thermochemical equations look like this. So you have an enthalpy of a chemical reaction, which is delta H. Okay, what is the delta H for the combustion of 11 grams of methane? With excess oxygen, that just means you have a lot of oxygen to go around. The first thing I'm going to do here is I'm going to balance it. 1 carbon, 1 carbon. Do the carbons first, then the H's. 4 H's, 2 H's, put a 2 here. Then do the oxygens last. 2 here, 2 here makes 4, put a 2 right there. Okay? So this means that for every 1 chemical equation like this, you're going to give off negative 802 kilojoules. Okay, I'm going to add another unit here. I'm going to say for every mole of this chemical reaction. So for every 1 of these squares, this reaction, you're going to get that. For every 2 of those things, you're going to get double that. Okay, so to start, you're going to write down the given 11 grams. 11.0 grams of CH4. And in the end, they're asking for the delta H, or the heat. So the heat is going to be in kilojoules. Okay? So first I'm going to change this grams to moles. Gram CH4, 1 mole of CH4. I'm going to do the math here. Carbon is 12.01. 4 H's is equal to 4.032. Common place value 14.04. Okay. The reason I converted to moles is because of this. I know that for every 1 mole of CH4, I'm going to drop the mole CH4, and this number came from that equation, okay? For every 1 mole of CH4, I'm going to give off this much heat. Okay, so this one came from the equation, and this heat came from the delta H. And that's it. All I have to do is do that math. When you do that math, it is, I'm sorry, this is not 14, it's 16. I'm going to get 551 kilojoules. So what this means is if I use 11 grams of water, I'm going to give off, oh, it's going to be negative because of the negative sign there. I'm going to give off 551 kilojoules, which makes sense because a mole is about 16 grams. I have more than a mole or less than a mole? I have less than a mole, which means I'm going to make less heat. Okay. You can also do the same equation. You can start with oxygen, grams, go to moles of oxygen. But instead of putting the 1, you're going to put 2 moles of oxygen and will give this much heat. So when I say mole of the reaction, that means this is how much heat you'll get for every 1 mole of methane, 2 moles of oxygen, 1 of these, and 2 of these, and so forth. It matches this equation.